Hello and welcome back to High Peak Education. Thank you for watching this video. For this particular video, I'd like to perform a centripetal force calculation. That is to say, given a speed, a radius, and a mass, I'd like to make some calculations about centripetal force, static coefficient of friction, because let's assume a car is on a circular track being held in by a road, and also calculate one other property. Okay, so let's imagine what's going on here. So we're going to reuse a car from a previous example that I showed, and with a radius of 500 meters and a linear speed of 25 meters per second. Remember, that was about 56 miles per hour, and a mass of 900 kilograms. So it's a modest-sized car in terms of its mass. A, what is the centripetal force magnitude, Fc, acting on the car? B, what is the minimum coefficient of static friction, mu s, between the tire and the flat road? C, what is the angle theta at which the fuzzy dice hanging from the rearview mirror makes with the vertical while the car follows the curve? Okay, so let's deal with each of these problems sort of one at a time. In fact, part A is basically a review from what we did in a previous video. So if you recall, we said that the centripetal acceleration should be v squared divided by r. And we said that this is v, the velocity, this is r, the radius, and we calculated 25.0 meters per second squared divided by the radius of 500 meters. So when you calculate that, you get 1.25 meters per second squared. That's in a previous video. You can check that. Well, I'm not going to put a box around that because that's not exactly what we're looking for in this problem. We're actually looking for the centripetal force. Now the centripetal force, which is the magnitude of the net force when the object is turning, is mass times centripetal acceleration. So that should be 900 kilograms multiplied by 1.25 meters per second squared. Okay, so let's go ahead and multiply those. Okay, so this is, let's see, 900 times 1.25. Okay, so that's 1,125. Rounded to three significant digits would be 1,130. Okay, so centripetal force, 1,130 newtons. Okay, so again, we're rounding because of significant digits. We believe that there's 1, 2, 3, 1, 2, 3, 1, 2, 3 significant digits. All right, fine. So that takes care of part A. Now part B says, what is the minimum coefficient of static friction between the tire and the flat road? So what I mean by minimum coefficient of static friction, remember, if the static friction is actually larger than what is presented right now in the car's current situation, we're saying that the car is moving slower than would be the maximum speed to just barely start to slide off the road. In other words, if this is the minimum coefficient of static friction, then mu of s is at its maximum value if the car is going exactly at its fastest speed to barely be held on the road. But anyway, let's just go ahead and solve for this mu sub s. So I'll do a brief little sketch here. So you can imagine if this is part of the curve, okay, and the curve has, a certain radius out here, okay, so, and here's the car. So this is sort of like a top-down view. Oops. A top-down view. So we're looking sort of on the car roof here. If this is the radius, and then we have the car here, so the four tires are sort of under here. Again, we're just sort of sketching it. And then the idea is that the force is the friction force. So if the friction force is in this direction, towards the center of the curve, how do I know that? Well, the force of friction static is the only force that's holding it on the road towards the center. Okay. By the way, we're not really worrying about the vertical direction here, like normal force and weight and things like that. So, in fact, you might even be interested in drawing the positive radial axis this way towards the center. So you could imagine maybe even a radial axis like this. But the reason that's important is because if we were to do Newton's second law, the sum of the forces in the radial direction, the force of friction static is our only force. And just like we talked about many times in Newton's second law problems, we add up all the forces from the free body diagram. In this case, it's only the friction force. And that equals the net force on the right-hand side. But the net force, in this case, is the centripetal force. Remember, this is the net force. Now remember, net force never goes on the free body diagram. But you could sketch it over here if you want to remind yourself that the net force equals the centripetal force. And we know what that value is. That's this right here. Okay, so let's go ahead and see if we can write an expression for the force of friction static. So the force of friction static, I believe, should be mu s times the normal force. But the normal force, let's just go over here for a second. The normal force should be upward. Normal force should be upward. Okay, so the normal force should be upward while the weight is downward. So the weight, mg, should be the exact same size but the opposite direction of the normal force if it's on flat ground. These single hashes are meant to indicate that these arrows are meant to be the same length, even though I didn't maybe sketch it perfectly. So this normal force can be just replaced with mg because we have equilibrium in the vertical direction. We have equilibrium in this vertical direction. So what do we have here? We have this is equal to mg, and I think we can go ahead and solve for the centripetal force. Okay? So I'm switching just to the black color, but hopefully you see where the vectors are and so on. But mu s should equal F sub c divided by mg. The centripetal force divided by the weight in this case. So let's put the numbers in. The centripetal force was, let's see, 1,130 newtons, and then mg should be the mass of the car. So this is the m. 900 kilograms times g on Earth. We assume that to be about 9.8 meters per second squared. Okay. So let's use the calculator to get this value. So I'll turn it on, I'll clear, and then I'll do alpha F1 to get this stack, n over d, numerator over denominator. And then I'll do 1130 divided by, oops, sorry, I don't need the divided by because it's already there. Delete, there we go. And I'll just go to the bottom of the stack. 900 times 9.8. Enter. Okay, so that's about 0.128, I should say. So this is about 0.128. Okay. By the way, remember, mu s is unitless because this is newtons divided by newtons. So this is our answer. Our answer doesn't have any units. By the way, also, that's the same value we got as far as the number of G's in the last video that I did about this car, but that's sort of serendipitous. I haven't figured out an exact reason why that is. Okay, how about part C? Part C is, what angle does the fuzzy dice make in the rearview mirror while the car follows this curve? So imagine that if you're in the car and the car is being held in towards the center, you could imagine that the fuzzy dice go outward toward the outside because you can imagine they have sort of their own inertia. But when the car moves inward, they're less connected to the car. They're only connected via the hanging. So I think that if I was to sketch the ceiling and what the fuzzy dice might look like in terms of a free body diagram, it would probably be something like this. So if this is straight down vertical, we should be able to sketch the chord, and I think that the fuzzy dice will hang, and let's give the fuzzy dice maybe the 5 is facing you. Okay, so this is the center of the fuzzy dice. Well, you could take a look at this object and look at all the forces on it. Okay, so let's in fact look at all the forces on it. So a free body diagram is helpful. So I think the tension force goes up this way, up and to the left. Excuse me. So the tension force should be like so. That's some sort of angle. Okay, so that's the tension force. Let's call it Ft. And then we also have, I believe, the weight straight down. Okay, now the weight, let's see. We don't actually know what the mass of the fuzzy dice is, but let's see if we can sort of get rid of it. Okay, so there's the weight. So this is m dice times g. Notice it's not the same m as before. It's not the mass of the car. And by the way, let's go ahead and label the angle. So the angle is theta here, with reference to vertical. Okay, so then that means, I think, if I reference another vertical line here, this is also theta. So that's the angle that the tension force there makes with vertical right there, like so. Okay, so let's go ahead and look at the forces along each axis. So let's look at the sum of the forces in the x and the sum of the forces in the y direction for this fuzzy dice. Now, by the way, as soon as we start doing x and y, we should have axes labeled. So let's call inward positive x. And that's because inward is sort of related to the inward part of the car here. So inward, let's call positive x in this case. Positive x direction. And let's call, let me do straight line, positive y direction. Okay, so with the x direction, I think this tension force should be decomposed into its components. So I'll break that out as well to examine that in a little more detail. Okay, so there's the tension force, and this tension force should be made up of two component vectors. Again, this being theta here again. So I think that this side is opposite, so that's Ft sine theta, which is across or opposite from theta, and then this component right here should be Ft cosine theta, because it's adjacent or next to this angle theta. So Ft sine theta is this x component, so that's Ft sine theta. And by the way, because I have the blue color out, why don't I just label in the y direction, the positive y direction is Ft cosine theta. Okay. Now, in the y direction, I think the only other force is the downward force due to the weight. So that's minus m dice times g. And let's go ahead and see what this equals to. So, on the left, or sorry, in the x direction, the fact that the dice is deflecting is due to the fact that the car is accelerating. So centripetally accelerating, in fact. So I think this should be m dice times the centripetal acceleration. Okay, so you got to think about that. The dice has inertia, it deflects out, but that's only because the car was accelerated inward centripetally. In the y direction, I don't think the dice is moving up and down as long as it stays at a constant height. So this should be 0. Okay. Now we have two equations, and we want to look for the angle of the fuzzy dice, theta. Okay. So what I'm going to do is I'm going to copy these two equations onto the next board, and we'll go ahead and pick up from there. So now let's propose our plan of attack. Now that we have these two equations reproduced, looks like in the transposing, the part of the top of the f got left off. So let's call this equation 1 and equation 2. So the thing is, theta is what we want to know. Now, consider that ft is unknown, and then the mass of the dice is also unknown. We do know the acceleration, and we do know g. So let's see, first of all, let's see if we can replace ft. So try to replace ft, because we're not interested in the tension force, and we're not asked about it, and it's in both equations. But see if the mass m dice cancels. Now, hopefully you recall, in many Newton's law problems and in many conservation of energy problems, the mass does cancel. So let's see if we can get that to occur. So I'm going to suggest let's solve equation 2 for the tension force and substitute it into equation 1. So I'll write that down. Solve equation 2 for tension force, and substitute into equation 1. Okay. So let's do that, in fact. Okay. So let's see what we get. What we get is the following. Looks like we get, and by the way, I'm switching to black here. Previously the colors were to tell you about which vector, but here we're doing a bit of algebra, so I'm just going to do it all in one color, the black color. So let's add the m dice g to the right-hand side. So that's m dice times g to the right-hand side. And I think we should divide by cosine theta to get the tension force. And then again, this you could call equation 3 if you like, but equation 3 gets substituted right in there for ft, the tension force, like we said. So this is what we get. We get m dice times g over cosine theta times the sine of theta, okay, and that should equal to m dice times the centripetal acceleration. Now here's where some magic starts to happen. Okay, let's see what that magic is. Look at this m dice. See how it's on both sides? And everything's multiplied here, or divided. Everything's multiplied here. I think we can just cancel it. We don't know the mass of the dice. We don't need to know it. But then also we have sine theta over cosine theta. And hopefully you remember what that trigonometric identity is. In fact, that is exactly the tangent of theta. So this is g times the tangent of theta is equal to AC. Now, we should actually take we should solve this for theta. So we need to divide by g. So tan theta is AC over g. And then theta is going to be, theta is going to be the inverse tangent of AC divided by g. Now, by the way, AC divided by g we actually did in a previous video, and I essentially already did that on the previous board. Because AC divided by g is the same thing as m times AC over m times g. So the m's would cancel. You get AC divided by g. So this right here is exactly, let's see, inverse tangent, same thing as arctangent of 0.128. Okay? So in fact, let me just make this an approximately, because we're going to approximately get this angle. Okay? So by the way, I didn't want to skip straight to this, because you wouldn't have understand where did that come from unless I went through the derivation of that this is inverse tangent of what we got in part B should give us our answer. All right, so let's make sure our calculator is in degree mode, and it is. So I clicked on mode. Now I'm going to do second quit. So let us type second tangent, and that's inverse tangent, of 0.128. Okay, so it looks like we've got approximately 7.29 degrees. Okay, so let us write this down. Approximately 7.29 degrees. Okay, and remember that's, deflected from vertical. Deflected outward from vertical. Vertically hanging down. Okay, because remember, degrees always means with reference to something, with reference to some zero. And that's what we have. Okay, so thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Thank you. Please share this with your social network, and I will see you in the next video.